So I1 and I3 are going to be the same. That's cool. What else do we know? What's going on here? There is not a lot of information to go on here. It's like I don't have the one thing that's what is the one thing that's really screwing us up in this question? That's not even the biggest issue here. The biggest issue right here is the existence of this circuit right here. If this, this resistor in the circuit right here. If this resistor is gone, and it's just a straight shot through here, we know what? About the voltages on these two branches. If this resistor is just a straight line wire, it's not there, what do we know about the voltage in these two branches? Not only are they going to be the same, because they're still going to be the same with this resistor here, but they're going to be the same and they're going to equal what? It's going to equal to this. If this resistor is not here, this is going to be this, which is going to be this. We can find the current here and here. We can add them together and we're done. The problem with this stupid question is that resistor right there. Because that resistor is there and I don't have the currents anywhere, there is only one way to proceed with this question. And the only way to proceed with this question is to draw the equivalent circuit. It's the only way to do it. So, first thing we're going to do is we're going to collapse these two resistors down together into something so if I redraw this, I'm going to call this R1. We know it is 6 ohms. This one right here, this one right here, I'm going to call RP. And this pretend resistor, the equivalent resistor, is going to be equal to the total resistance of these two in parallel. I was really confused by what was going on with the holes in your elbows, but now it makes sense. So to figure out what RP is, it's going to be 1 over RP is going to equal 1 over 2 plus 1 over 4. There is a dot there, believe it or not. That's 4.0, not 40. So then this thing's going to be 1 over RP is going to equal 2 over 4 plus 1 over 4 equals 3 over 4. So RP is going to equal 4/3, or 1.3 repeating. If I make a mistake, please somebody say something, but I'm pretty sure we're doing okay. So what that's going to allow us to do, because I know that my total voltage supplied is 20 volts, and I want to know what I3 and I1 are, those, because they're on the main branch, like they're not on a branch, they're on the main series of the circuit, I total is going to equal I1 and I3. So if I condense my resistors together to one monster resistor, I can calculate I total, which is going to equal I1 and I3. So to do that, we're going to use I equals V over R. The total voltage is 20. The total resistance we already have is 4/3. I'm going to leave that as a fraction to make my life a little bit easier. So my current is going to be 20 times 3 over 4, which is 15. That's not true. What happened here? 20, 2, 2, and 6. Oh, I screwed that up. Guys, come on. Zaid, you're supposed to stop me. Sorry. This is, RT is not 4/3. It's 4/3 plus 6. 4/3 plus 6 is 22/3? Oh, this is a gross fraction. I'm going to make this. How did I do that?
No, why?
Why did I do what? Because yeah, that. And sometimes the fractions work out really nice and I can just throw down an answer. But 2.7 is gross. So my I total is going to be 20 divided by, what's 7.3 repeating? Yeah, see, that's where I want to be able to do it in my head and I can't. 20 divided by 7.33 repeating, 2.7. Angelina, does what I did up to that point make sense? Okay. So that gives me this. It gives me this. I can't figure out this until I know what the voltage is here. So I have to figure out now what the voltage here in 1 is. So V1 now is going to be I times R. R is 6, I is 2.7. So my voltage drop here is going to be 16.2, which means if this resistor eats up 16.2 volts, each of these branches needs to be able to drop down how much? Well, 20 minus this. Because it doesn't matter what path you take, you have to be able to drop all of the available voltage. So it's going to be 20 minus 16.2 should be 3.8. So my voltage drop here is going to be 3.8, and my voltage drop here is going to be 3.8. Which allows me to now go find I2. I2 is going to equal V3 over R3, 3.8 over 4, better be 0.91. I got 0.95, but that's probably because I rounded differently. If the answer key says 0.91 and you got 0.95, I'm going to give you that. Because this actually should have been rounded a little differently. But that's the procedure. Does that make sense? So it's actually a little bit of both techniques that I told you about. I said, find everything. Well, or draw these equivalent circuits. Well, to find everything, you have to draw the equivalent circuit to give you the total current on the main branch. And then we have to find this voltage, to find these voltages, to find this current. Anybody else? Questions about any of the homework? 18. 18 is a beautiful one. Let's talk about 18. What are you even looking for? R3. Where's R3? That guy. We want that resistor. We want, where's I2? That guy. I3 and I4. There's one of these that's very easy to find immediately. I3, because it's also on the main branch, and we know I1 is 3. Because the main branch goes, it splits, but then it comes back together. So these two currents have to be the same. So I3 is nice and easy. I3 has to be 3. Now, do you want to see the I can reason my way through this all awesome, or do you want to see the actual calculations to prove without a doubt that we're right? Because eventually the goal is going to be for you guys to start, you're gonna reason your way through these things and be like, oh, I don't have to do calculations because it must be this way. The danger being if I show you that, then we change the numbers so it doesn't work out quite so nicely, and then we're screwed. Okay, I'll show you both ways. I'll show you how I reason it, and then I'll show you why I'm right. So the first thing to recognize here is there's a relationship between these two resistors. What is the relationship between those two resistors? Connor? Parallel. They're in parallel, and what's another relationship? One is double the other one. So if this one is double this one, how does that tell you about how the currents are going to split? How much more? Double. So this one, because it's half the resistance, is going to have twice the current as this one. And I have 3 going into that junction. So can I break 3 up into 2 numbers that add together to give me 3, that one is twice the size of the other number? Sorry? 1 and 2. So the current here is going to be 1. The current here is going to be 2. Because of just the fun relationship between those two resistors. I'll prove it to you in a sec. If I know that this is I1 and this is I2, Now we can go through and we can find the voltages everywhere. And I need the voltages everywhere because I need to know how much voltage is eaten up by these things so that I can figure out how much voltage is left for this guy so that I can go find this guy. The other beautiful thing is that these two resistors are the exact same system as these two resistors. So this guy here is also going to be 1 because this guy here was 1. So using just by noticing how the numbers work out, I'm able to make some deductions here. I'll prove it to you the long way later. Now, because I know these things, I'm able to find some voltages. I know that V equals I times R. So voltage here is going to have to be 20, and so that means voltage here is going to have to be 20, which means my voltage here is going to have to be 20, which means my voltage here is going to have to be 20. But careful with how voltages show up in parallel. In parallel, they don't add and split like current does. How voltages work is it doesn't matter which path you take. It has to be the same step down in voltage. So the thing you want to recognize is between this point here and this point here, I have lost 20 volts. It doesn't matter which path you take. That's what's been eaten up. And from this point here to this point here, I've lost another 20 volts. Doesn't matter which path you take, you have to go down 20 volts. So in total, these two parallel circuits eat up how much voltage? 40, which means how much voltage is left here? 50, because there's 90 to start with, and I lost 40 through these two. So my voltage here is going to be 50, so my resistance is going to equal my voltage divided by my current, R equals V over I. So my voltage there is 50, my current now is 3. 50 over, well, 48 over 3 is 16, so it should be 16.6 repeating. Which rounds to 16.7, and we're good. That's the I noticed there's a cool relationship method. And the quicker you can get yourself there safely, the better you're just going to be with circuits in general. But there is a much more concrete, straightforward way to do this, and that concrete, straightforward way to do this is to equivalent circuit this ugly monstrosity. So we're going to do that. So that's, I've solved it one way. We cool with that? Okay, here's the other way. The other way to do the exact same problem is to split this thing up into its equivalent circuit. This guy right here I'm going to call RP2, and this guy over here I'm going to call RP1, and this guy down here is my R3. My voltage is 90, and what is my, actually my total voltage is 90. What's my total current? It's 3, because the current on the main branch was 3. So now we got to go through, we got to figure out what RP1 and RP2 are. So this is going to be RP1. So 1 over RP1 is going to be equal to a 10th plus a 20th, which is going to be 2 over 20 plus 1 over 20. So RP, 1 over RP1 is going to equal 3 over 20. So RP1 is going to be 20 over 3, which is gross. Thank you. Which is the same thing that this one over here is going to be, because it's the same two resistors. But otherwise, I would have to calculate this one the same way I did this one. We cool with that? Okay. So RP2 is also 6.6 repeating. So I've got this guy here is 6.6 repeating. This guy here is 6.6 repeating. Now I can use my V total and my I total to find my total resistance. My total resistance is going to be 30, because RT equals VT over IT, and that's 90 over 3, so RT has to be 30. but we know RT is going to have to equal RP1 plus RP2 plus R3, because these three are now in series. So I know that 30 is going to equal 6.6 repeating plus 6.6 repeating plus R3, which is going to make R3 equal to 30 minus these two, which is going to give me 16.6 repeating. The same thing we ended with over here is the first one we have to find here. Well, now I'm going to go back, and I'm basically going to do it the exact same way I did before, but backwards. I found this resistance, so now I'm going to use the fact that V equals I times R. This resistance times this current, 3 going through here, is going to give me my 50 volts here. If this thing uses up, so V3 now is going to be 50 volts, which leaves me with 40 volts that have to get eaten up here and here. Well, voltage is current times resistance. My current is 3. My resistance is 6.6 repeating. 6.6 repeating times 3 is 19.9 repeating, which is 20. So VP2 is going to be 20, and VP1 is going to also be 20. And so now I've got my voltages for each one of these is 20. And then I can go back, and the last thing I'm going to find in this case is going to be I4. So current I is equal to voltage divided by resistance. My voltage is 20, my resistance is 10, so my current is 2. So by building the equivalent circuit, I did it the exact opposite direction as if I was just going to reason my way through this. Both of them work. The only way the first way works is because these two resistors are nice. And that will sometimes be the case, and but won't always be the case. Did all of that make sense? If I lost you anywhere, there's a video that you can either speed up or slow down when it's posted to YouTube. Or I'll happily go over it again after school. But that might be the gnarliest thing I can give you, I think. Well, I could change those voltages and then the resistances, and then you're really hooked. Do I give you anything meaner than that? Oh, there's some graphs coming up here for you, Naya. Yeah, there's some fun questions coming up here in the review. It's good stuff. Like this one, this bad boy, he's pretty. Nail, look at what's coming here. That guy, he's lovely. It's not horrible, but it's certainly not nothing. So like, there's a lot back here, and all the things, but it's all just practice. There's some graphing here. Look at that lovely graph. So, anyway, comments, questions, concerns. Anything else from the homework you want me to go over? Okay. Then let's start the last lesson. Let's see how far we get. Flip the page. Electromotive force, which it's unfortunate in how it's named, because electromotive force is actually not a force. It's yet another thing where, like with big things, it's easy to be like, oh yes, that's a car. Oh yes, I pushed my car, and Newton's like, oh, I pushed the car with this force that produces this acceleration. Nice and easy, I can see it. But all of these things in electric circuits, these guys are like, ooh, there's things going on here. So it's the positive things that are going to move, because we like positive things, so they must be the things doing the moving. And then we realize later, actually, what's doing the moving? The negatives. Okay, so we're totally backwards there. But we'll just recognize that we're backwards there, and we're just going to go for it. Then they come up with these other things. So they're like, yeah, there's more concepts here. We're going to call this thing electromotive force because it's an electric thing that provides a force to these other things. And then we go a while longer, and we learn, oh, actually, this has nothing to do with providing a force. It just provides a potential energy difference. And it's the fact that there's a difference here, like potential gravitational energy, where like it's not a force, gravitational potential energy. It just provides a circumstance where something might fall. Yes? Same thing with electromotive force. we're like, oh yes, it's the electromotive force, it makes things do something. Like, well, actually, no. It is just a circumstance that gets contrived so that something else is able to do something. And so we call electromotive force, and it's actually wrong, but that's okay. We're going to learn about it anyway. So let's go. Electromotive force. We know that a battery is a source of potential difference, and we call the potential difference of a battery voltage. We also call it, it's also considered like electrical energy. When not connected to a circuit, there is still a potential difference in those terminals. Even though there's not a circuit there, you could hook up a voltmeter and you could measure the voltage difference between the positive and negative terminal. Yes. If you have to, go. Probably not a great time, but you can do what you got to do. Before we called voltage, they called it electromotive force. Which we abbreviate as EMF. And the symbol whoops, that's really hard to read if you're way at the back there. Symbol is something, and the units are something. The units, actually, we know what the units are, because this is a kind of voltage. So the voltage units on EMF are going to be what? It's exactly what you think it should be. V, volts, yes. If you had to give this thing a letter to represent the concept, the one you would probably want to give it is what? E. But E gets taken up where? It gets taken up in energy. Thank you, whoever said that. Jasmine, if that was you. So we can't use E. So it would be great if there was another language close by that we could just steal their E that doesn't look exactly like our E, and we'll use that E instead. So they jump over to the next closest available language, Greek. And they jump, actually, well, the original language of science was Latin, so Greek is pretty close. So they jump over and they take that Greek letter epsilon. That's epsilon.
It's not like
It's just fancy E though.
it's like some math symbol too, isn't it?
Yep. Yep. It's just a curly E. Looks like a backwards 3. That E specifically represents the voltage known as electromotive force. Despite the name, this is a potential difference. Not, underline that word, a force. Even though we call it electromotive force, it's not a force. And this screwed with me when I was a physics student in high school. But you just got to recognize that this was made up, like this was developed, not made up, but this was developed by a bunch of guys who really had no idea what was going on. And it worked, we just had to change some of the names. For example, a car battery has an EMF, an electromotive force of 12 volts, and the lithium battery that you could pull out of like the back of a watch or something has an EMF of 1.5 volts. A AA battery, AAA battery also has an EMF of 1.5 volts. Or we would say that the potential difference of these batteries is 1.5 volts. However, as soon as a battery is connected to a circuit and current flows through it, the potential difference across the terminals is actually always less than the total EMF.
Can I guess why?
You can guess why. Would you like to guess why?
Yes.
Guess why.
Okay, so when there's resistance, it kind of takes off the voltage a little bit, or it takes away from it.
That is true, but what resistance are we not taking into account? Because the circuits that we've drawn, we say, okay, well, this is a 12-volt source. This resistor uses up this much, and this resistor uses up this much, and this resistor uses up this much, and we're back to 0. What this is saying, and maybe I'm not being as clear here as I would like to be, what this is saying is that a 12-volt battery doesn't actually supply 12 volts once it's connected to a circuit. It provides a potential difference that is a little bit less than the EMF that's printed on the side of the battery.
Because it's not all contained in the battery now, it's part of the circuit as well.
Nope.
Okay.
The thing that we're not taking into account, this is due to the fact that every battery has internal resistance. There is something about the construction of the battery that resists the flow of electrons. And there is nothing we can do to get rid of this. Every battery has some measure of internal resistance. If you could create a battery that had zero internal resistance, that would be amazing. We can't. It's not possible yet. Because of this particular, it's called an internal voltage drop. The terminal voltage is always less. Should just be regular less than the EMF of the battery. So the battery will have 12 volts printed on the outside. If you tested it with a voltmeter, come on in, Manuel. You tested it with a voltmeter, it would read 12 volts. But as soon as you hook it up to a circuit, you're actually getting less than 12 volts. So what this does is it gives us the concept of terminal voltage. Terminal voltage, you're going to love this, is VT, which looks a lot like total voltage, but it's not total voltage. It's terminal voltage. And that's going to be equal to the EMF minus whatever the current is times little r, and little r, I'll go E equals EMF, I is equal to total as the current, I'll just say, and little r is what we call the internal resistance. There is a reason why up till this point I've called everything big R1, big R2, big R parallel, because little r is reserved for the internal resistance found in these batteries. This I times R piece, I'll do this in a little bit here, this IR piece is how we calculate the internal voltage drop. So the terminal voltage is equal to the EMF minus the internal voltage drop is what this whole little expression is right here. This is going to lead to eventually, never mind, I won't say that, forget that. If the battery is not connected to a circuit, there is no current. So VT equals E. And the only way that this would ever show up is if you actually used a voltmeter to measure across those terminals. Because if you remember, when I first introduced voltmeters way back at the beginning, voltmeters are built with an incredibly high resistance so that almost no current gets through, because all you want to do is measure what the terminal voltage is. And so when you measure it, it's going to read like V is equal to the electromotive force. But as soon as you hook it up to the car and turn the car on, now you've got an internal resistance that you have to deal with because you're allowing a current to flow. Hopefully that makes a little bit of sense. So, there is a diagram. We're going to now tweak our diagram. Where's my mouse? There's my mouse. We're going to tweak the diagram now for a circuit. Before, our circuits just look like this. I'll draw it on the side here. This was the old diagram. We had our source, we had our resistor. Back to the beginning. Excuse me. This was our original diagram. And we say, well, that's a voltage source, and away we go. But that's not accurate. What we're going to do now is we're going to do this. I'll zoom this in a little bit here because I don't have a ton of space. We have this. We still have our voltage supplied by the battery. This guy is still positive. This guy is still negative. But we've got now a tiny little resistor on the inside here, little r. And this whole thing is contained inside a dotted line that looks an awful lot like what? A battery. So we recognize that this diagram picture that we had here to represent a source, we're replacing it with this thing that actually looks kind of like a battery that has our EMF and our internal resistance separated. And then we get the rest of the circuit. And this guy here is going to be big R. This guy in here is going to be our electromotive force. But if I tested the voltage from terminal to terminal, this thing would give me VT. So R here is the external resistance, the internal resistance is little r, the EMF is that epsilon there. So this actually does a little bit to explain to us why a battery actually goes dead. What happens to cause a battery to die? Nope. That's one option. That is the incorrect option. What is the other option? Nope. A battery goes dead because the internal resistance builds until I times little r is equal to epsilon. And then you've got VT equals 0.
Which you're saying the battery could technically go on forever if it didn't have that.
If there was no internal resistance, the battery would go on forever. So the law of thermodynamics, which we don't actually teach you in this course, and will never teach you in high school, is dictates that there is no it is impossible to build a battery with no internal resistance. Yes.
Is there a way to figure out how long it would take for that battery to?
No, not necessarily. Not unless you looked at the life of the battery. Like, you'd have to study the battery over time. And no, there's no way to know. So, for example, let's do an example. A 12-volt battery has an internal resistance of 0.22 ohms. Not a very big resistance. What is the terminal voltage of a battery when a current of 3 amps flows through that battery? Well, we've got a few things here. We've got a 12-volt battery. We've got an internal resistance of 0.22, and we're asked to find terminal voltage. So VT is what we're looking for. We have little r, the internal resistance, is equal to 0.22 ohms. We're told that a current is going to flow through this thing of 3 amps. So what is this value representing? Where is this 12 volts coming from if we're asked to find terminal voltage and we're given these two things? This voltage must be that other voltage, EMF. The EMF of the battery is 12. So then to find terminal voltage, we know that VT is equal to epsilon minus I times little r. So that's going to be my 12 volts minus my 3 amps times 0.22, giving me a terminal voltage of what is the battery actually supplying? 11.34. So the calculations aren't overly difficult. it too if you want. Calculations aren't hard. You just got to recognize what pieces are actually related to what concepts there. I am going to stop here because the bell's going to go in 2 minutes, and the next thing I'm going to introduce is probably going to make you upset. Because it really bothered me when I first learned about it, and so it's better to do that at the beginning of a full class than right at the end of this class. So we're going to there's something called back EMF. That's what's coming next. It's what happens when you recharge a battery. So we'll get back there. We'll start that tomorrow. There you go.
Wait, so when you recharge the battery, are you simply
Tomorrow.
just kind of getting rid of the
Tomorrow.
resistance that's built up?
Tomorrow.